So good site investigation leads to better designs every time. That is every time. It does lead to better designs and more efficient design and construction process. So today we're going to share some of our experience on that. So today's topic is site investigation. The overall objective of a site investigation scope, I suppose, is to gather the information needed to carry out a task of some description. In our case, that's usually site investigation to carry out design work. And it could be investigation through surveys, such as refurb and demolition surveys or R&D surveys. It may not be based via desktop surveys. It could be site-based, so based on ground-based investigation as well. So we look at boreholes or lab tests, for example. Site investigation is really important as it enables us to really understand the challenge at hand, be that the type of ground that we're working with or the type of structure. So if we have a soft or a stiff clay or a peat or bedrock, we could have steel or concrete or precast structure that really does govern the construction process or the demolition process that we're working with, and what that end up solution is going to look like. Because if we know the challenge that we're tackling, then we're able to provide that correct solution, that efficient solution. And the better we understand the challenge, the more efficient or cost effective or safe the solution will be, which is really important. So the better we understand the challenge, the more efficient, the more cost effective, or the safer the solution will be. That's essentially what we're aiming for, the main philosophy. So site investigation is relevant to temporary works really as much as it's relevant to anything, any kind of design process or understanding process in the construction industry. Every construction or demolition project is the same. If you strip it right back to the very principle of philosophy of what we're doing, there's a challenge and we need some kind of solution to overcome that challenge. So we've got a few examples here, just to pick them out of the blue, really. We've got Eggborough Power Station, the pre-weakening and explosive collapse, control collapse of the cooling towers there. We've got a removal and restoration of a timber signalling box in Norfolk. We've got facade retention of a scheme in Leeds, the Majestic, and then we've also got some foundations for mobile crane operations. All of these jobs required site investigation to some extent to enable the projects to go ahead. We're going to split this presentation up into two sections, really, this topic into two sections. I'm going to run through the structural site investigation, and Adam's going to take us through a case study based around that. And then Richard is going to take us through some geotechnical site investigation. So first of all, what is structural site investigation? So we've established so far that with site investigation, we're trying to gather information about something to enable us to understand what we're working with. And with structures, we're often required to justify them being loaded in different ways for some new purpose, or partially demolished, which then puts different stresses and different loads on the structure. So we therefore need to understand how the structure is likely to behave when we're trying to use it in this new purpose. And this behavior can be understood through site investigation, or SI. And we need to uncover from the structural form of the building and find out the construction details, to either confirm the details that we've shown in archived drawings, or sometimes just to find out what there is, because more often than not, there are no drawings or archived drawings available of the structure. So we can see here on these photos that we've got some column centers shown in an area with some breakouts carried out, exposing the rebar and the concrete beams and the slabs and the walls. That's the kind of thing that we do just to verify information that we've got from elsewhere. This is what some good site investigation looks like. And it's good because the trick is to get enough information to understand the structure without destroying too much and causing some significant structural issues. So a small hole, a very small hole, like a core, for example, with one rebar shown, that will tell us the thickness of the slab and that it's reinforced, but it doesn't tell us the centers of the reinforcement, and it doesn't tell us whether there's rebar going the other way, for example. So it is a balance between carrying out enough of a breakout to establish exactly what the construction is, but not too much so that the structure becomes unstable. For example, You don't want to just take out a whole column to find out what the rebar is, because the column is going to be supporting a significant amount of structure and may lead to a collapse. So it's a balancing act, really. Here's an example where I've been out to site to determine the weight of a conveyor structure, which was going to be removed in a cut and lift, proposed cut and lift sequence. Because I was involved early on the project and understood the scope of what was going on, part of this conveyor was going to be removed mechanically with a high reach excavator. And then the rest of it that was sat over a road would be cut and lifted. So I asked the contractor if they could keep a section of that conveyor so I could measure up accurately. And then that would give us a very accurate weight for when we're doing the takeoff and the lift of the structure of the road. That essentially removed the risk of working at height. And it also meant that we could get a very accurate weight of that structure without any guesswork, which reduced the crane size, reducing risk, reducing the cost of the crane and rigging up time, etc. There's many dividends to come out of planning ahead and thinking about what we're trying to achieve and planning for that. Depending on the scope of the site investigation works, it's sometimes necessary to provide a detailed plan of the proposed site investigation. We've got a couple of examples here. It's more relevant on more higher risk structures where it's really important to get it right first time. So on the left, we've got a simple location plan that I've sketched over, identifying some requirements. And on the right, we've got a more formalized drawing, which shows and details quite clearly the extent of exactly what we're expecting to be broken out, the number of floors and locations. This may well be documented in a report, which is quite a formal proposal and a formal feedback report, which isn't too common, but this would be on more high risk structures, or if there's a very clear outline site investigation requirement. On very simple structures, just some small sketches and photos would suffice. So something like this, where we've got a photo here of the structure. Pictures are fantastic. A picture explains 1,000 words, so they say, but there's some additional content that we require from here. So for these, for example, it's helpful to know that we've got steel structure or slabs or reinforced concrete, but we need to understand some of the geometry. So the size, the shape, thickness, the span, the materials, as depending on the quality of the photo, sometimes it can be quite difficult to see whether it's timber or concrete, for example, or plaster and concrete. So some annotations are very helpful in those cases. The location of the photos is also really important, so we can start to get to grips of the structure. So these same photos sketched on top of with pen, showing some of the geometry and location, would be really quite great. Site investigation plays an important part when working on existing structures, and it's really important to do so we can reasonably confirm that the structure is as per the archive drawings, if there are any, so if we're relying on them. And notice I say archive drawings and not as-built drawings, and that's because the number of as-built drawings that are stamped as built that we've seen, and then when we've actually gone onto site and looked at what they've actually built, it's significantly different. So it's a bit of a misleading term using as built. So we tend to use archive until it's been confirmed. Site investigation also leads to mitigating risk from something called latent defects. That is a fault that could not have reasonably been spotted during a thorough inspection. These can become a problem when working with existing structures, and essentially it's don't assume something is there when it may not be. Here we've got so I'm going to go through a couple of examples. So here we've got the roof of a large steel structure, which is a gas holder. This was a roof structure that was going to be used as part of a strong working platform. So it was really important that we understood as much as we could about this circular roof, which had trusses coming out as radials. We needed to analyze the structure quite in detail so that we could understand its load capacity. That meant that we had to do a very thorough visual inspection of the structure to make sure it conformed with the drawings that we had of the structure. Upon this inspection, we noticed that there was a latent defect, and as you can see as the top chord that's deformed as it bulges out there, and we believe that this was damage from an unexploded bomb during the Blitz, which just shows why it was a good call to empty these gas holder structures at that time during the Blitz. But this was only really identified through that thorough visual examination, and therefore that meant that we could design suitable strengthening or just make sure we carried out a very detailed check about that structure to make sure it's quite low utilized, or put the strengthening in. So it's important to understand that that's there and what we can do about it. Another latent defect here is where a precast beam collar, which I've shown in green there, should have been seated on the dowel, which is highlighted in red. The drawing said that the beams are supported on dowels, and hence you'd think, well, that's fine then, because we've got some longitudinal resistance if we were to start putting some load into those precast trusses. However, in this instance, this one would not. So that was helpful that we picked up that in a thorough investigation. I'm going to tell you a little bit about large panel system structures, or LPS structures. And the reason I've chosen this to run through is because these, the latent defects associated with these are significant. The risk associated is significant. We've got a presentation on our YouTube channel which covers this topic of LPS structures in quite some detail, but I'm just going to go through the kind of headline acts. They're essentially large panels all put together and stitched together in situ with concrete strips, and they were put together very quickly following the after the World War II housing crisis, just to get some houses on the and some houses available for the market. And these structures essentially rely on gravity to keep them together, so they're all stacked up and tied together with rebar, which links through with loops, and the overlapping of those loops that project from those panels are all linked together with some dowel bars, and then they're cast in together. As you can imagine, that these loops, if they were missed, then the structure is weakened considerably, and what's worse is that those missing loopholes, they're masked by concrete, so that you don't even know that they're missing when you were to inspect them. And you can see as this structure here, this is a structure that's partially demolished. You can see that there is a presence of a piece of rebar going through that stirrup, that loop. So that meant that that was connected to the one next to it. So that's exactly what we want to see, but it's not always there. So if we take an LPS structure and as an example and demonstrate what we can do when we have a known risk associated with latent defects and how site investigation can assist in this situation. So on the whole, it's to have two things really. It's a very in-depth understanding of the structure, and that is garnered from site investigation that's been carried out previously, perhaps, and a desktop survey. And then also to supplement that with some further site investigation on site, intrusive site investigation. So that is breaking things out and actually having to look at exactly what we've got, where we've got it. And then the other thing is to have temporary works design and demolition planning to eliminate risk and from both overloading the structure and the structural instability as well. So this includes choosing the right methodology in the first place too. So it's two things really. One of the risks here is what exactly are we working with? Extensive site investigation. So we use this to ensure that we've got a really good understanding of the structure. On this project, we worked very hard with the demolition contractor to establish quite a robust schedule of investigations up front so that it could cost that in accordingly. And this investigation scope would hopefully identify how well the structure was put together. I.e., was it a Fred in the shed kind of company who just threw it up in no time? Thus, was thinking, well, if that's the case, then it's very likely that there's going to be missing loopholes, etc. Or was it really well constructed to give us a bit of confidence? And in this case, the structure was constructed relatively well. There were no instances where panels failed prematurely due to these latent defects. So on the left-hand side, you've got one of the floor planks, and you can see the pre-tension strands in the bottom face. There's also some concrete infill near the panel supports as well. And the concrete is there to really increase the shear resistance that you have the highest shear at the supports of those panels. So they filled those infills with concrete there. On the right is the panel to floor construction, and you can see that the loop has been captured with that dowel, which is exactly what we're looking for. Okay, and on to the second kind of part, because we're working with a structure which is so high, and in this particular location, it was very close to a high street environment. So the scaffold would encapsulate the structure, but then it leads on to another risk: is how do we, if we're thinking that the structure is okay, but still there's a residual risk that a panel could come apart because we can't hit every single connection in the whole structure. We need to think about what if there is a part that we've missed in that extensive site investigation that was carried out. Then we need to think about, okay, so what if one of the panel peels away, comes down? And when we're working in an environment where we are very close to a high street or network rail lines or some other risk on our boundary, then we need to design our temporary works accordingly. So the panels rely on the self-weight of the floor panels above to maintain that stability. So they're essentially being restrained at the head. And if we remove this, which we're going to do in the demolition cases, we're taking it top down, then we need some other kind of support system in place. And on this project, we utilized some simple raking props, which were bolted down to the slab and then to the wall. And then we designed that tension tie lower down just to prevent that panel from kicking out at floor level. And this system ensured that the panels would remain stable during demolition, but also that they wouldn't kick out on the floor. Without being sure that the structural makeup of the structure, we couldn't design suitable props that would ensure the operations. So we had to ensure something that was put in there was nice and robust. For example, you could overstress the structure by doing something that you think may be helping, when in fact you're actually making it worse. And that's what was helpful out of the site investigation that we got out of this project, that we knew exactly what we were working with. So that now that deals with the bigger stuff. How do we stop some of the smaller debris leaving on that site perimeter? So we're high up on the high street. It's really important to prevent small bits of debris, or small, like ejector, it's called, the small bits of debris pinging off, or a scaffold clip or something like that, falling from the height such as what we had here could have led to some serious injury or fatality. So we've got some scaffold screens installed, with also some boards down as well. And this is essentially encapsulated the structure to make sure that we were catching those smaller items. Another protection measure that we employed was to construct a proprietary deck in the area that was closer to the tower. This was a key thoroughfare through the city centre, so we were not permitted to close the walkway, so that we constructed a deck which encapsulated that walkway. So a combination of all these methods, working from the source of where the plant is down to the crash deck just above the public, mitigated that risk of falling objects and ensured safety on the public. So it's a two-pronged attack, really: understanding the structure and then using that understanding to design something that's suitable. So now that covers the protection methods and how we protected the public should any material fall from the tower. But that is quite a reactive method that doesn't really focus on the source of that hazard. And so another solution that we employed was to highlight areas where there were high risk and using risk zoning. So we identified red, amber, and green zones according to the risk in that area. And the red zones were carried out outside of normal shopping hours, whereas the amber and the green were carried out in the day, providing that the planned exclusion zones in the public zones were adopted. So that is the best way, really. It's trying to eliminate the risk where you can, using that ERIC principle of eliminate, reduce, inform, control, that hierarchical control of risk. So we eliminate if we can. If we can't, then we try to reduce that risk. Now that we've reduced it, we inform those that are going to be subject to that risk and control it through design. That's what we did here, right from the beginning, of understanding the structure and site investigation, and then implementing suitable methods during the works and execution. I'm now going to hand over to Adam, who's going to take us through a case study on how site investigation at the front end and throughout that project can really pay dividends later in the project. So over to you, Adam.
Thanks, Josh. Hi, everyone. I'm going to talk about a retaining wall justification design check, where essentially the site investigation determined the outcome of the temporary work solution. So a recent project in our office was the obviously justification of multiple retaining walls during the partial demolition of a structure. This structure was formerly used as large-scale retail buildings located in Kidderminster. And as part of the permanent work specification, the retaining walls along the east side of the structure and return walls were to be retained as highlighted in green. And these walls range from 4 meters to 10 meters in height around the perimeter. The partial demolition meant that the retaining walls changed from being a diaphragm-supported structure by the slabs to a cantilevered system, which was now fixed at the base. So this change required a new check on the wall stability against the active loadings from the surcharge and soil behind the wall in the new condition. So it was essential that at the start of the task, we set out the requirements for the site investigation needed for us to carry out the checks. So we needed to understand the structural properties of the walls, including the thickness, the reinforcement, and also the ground profile behind the wall. And this was before we began any kind of assessment. So we had access to the following site investigation. Some was already provided, like the 3D scan, and some was requested, like the core holes and trial pits. So the trial pits were carried out in positions adjacent to the wall to really understand the ground profile. We learned from the SI that the soil was built up from a layer of loose sand, which was overlying a denser sandstone material. This was consistent along the length of the wall, which really confirmed, which was confirmed through the trial holes that were completed along the length. Core holes were also drilled through the wall. This was to work out the wall thickness and the structural reinforcement details. And just like the trial holes, these were completed in multiple locations along the length and also at different heights to understand if the wall was consistent or not in its sort of build up. We could determine from the SI that the reinforcement was continuous between the slab and the wall at the base. Therefore, we could identify the wall as being a cantilevered structure from the base. The reinforcement was also present at the front and rear face of the wall. And the core holes also verified that the denser sand that was lower down was not actively loading the back of the wall. The initial assumption was that the full backfill soil height would actively be applying the load. However, the site investigation confirmed this was not the case and therefore influenced this design in a beneficial way for when we were doing our assessment. We were also provided with a 3D scan of the structure, which verified the SI that we'd completed and sort of gave us freedom to access at any time. And we could therefore jump into the model and get dimensions and distances to assist us within the checks. The assessment firstly consisted of comparing the existing stress conditions against the new stress conditions within the wall. As expected, the new stresses without the diaphragm supports from the slab were a lot greater. Therefore, we needed to carry out further checks on this wall. The retaining wall was checked in the critical failure mechanisms globally in overturning, sliding and bearing, and locally in bending, shear, deflection. We were able to justify the wall stability under the new loading while behaving like a cantilever from the fixed base. This outcome essentially eliminated the need for a costly and time-consuming design or remedial measures to be taken place. And this was to the satisfaction of the contractor and the client on site. However, in the absence of good SI on this project, a more heavy-duty basement propping scheme might have been adopted. Next slide, please. It was also recommended by ourselves to leave a bay of the single-story steelwork in place, which would contribute to increased stability, albeit not absolutely critical for the wall to work. We also proposed the tilt monitoring system at the top of the wall throughout the demolition, which had trigger levels, and these prompted actions based on the magnitude. So if deflection exceeded 6 mil and categorized as amber, a contingency propping design would be sourced onto site and only installed when deflection exceeded 10 mil and categorized as red. So through adding this monitoring on site, it ensured that if the wall began to excessively deflect, then we could implement a solution that was already designed. So in summary, the site investigation in this project was not just a formality, it was critical and a valuable step that ultimately led to a more efficient, cost-effective and safe solution for the temporary works, or in this case, no temporary works was required. The early consideration for SI within this project allowed us to make informed decisions from the start with a solid understanding of the site conditions. The site team also being cooperative and engaging with us ensured a smoother process when we were requesting for information. And this relates back to the famous saying of garbage in, garbage out, where if there's a lack of good quality information at the beginning of a project, the design output will also be of a similar standard. So preventing unnecessary remedial works. So in this case, a combination of the core holes and trial pits revealed the actual ground profile behind the retaining wall, which gave us accurate loading conditions. Without this geotechnical and structural investigation, the design might have been overly conservative and based on an incorrect loading scenario, leading to unnecessary temporary works and an over-engineered solution, which was based really on assumptions. So it emphasizes the importance of spending longer at the start of the project to address the SI requirements, and I feel this complemented the design check process, reducing risk and ensuring safety. So an accurate understanding of this structure and site conditions minimize the uncertainties within the design and any risks associated with the temporary works. For example, understanding that the wall cantilever from the base allowed us to analyze it appropriately and also tailor the SI requirements to the problem that we encountered on site. So thanks for listening to me. That's all. Now I'm going to pass you over to Richard, who's going to talk about some geotechnical investigation.
Yeah. So thanks, Ad. Now we're on to my part. Hopefully that transition was quite smooth. I think it went well. So I'm going to talk about the geotechnical side of site investigation rather than the structural side that Josh has already been through. So for every job that we end up doing, all the loads eventually come back to the geotechnical investigation. All loads have to go into the ground at some point unless you are in space for some reason. Interesting to do a temporary works design in space, not done one yet. But if anyone has one going, let me know. But in general, the typical kinds of temporary works we do are mobile crane positions where obviously you have a very high point load that goes into the ground at a point. So we need to know what's underneath that. In comparison to that, you've got the haul roads, the pile mats, the long slope stabilities that we can get on some temporary works jobs. Obviously, they are much longer and you need a more site-wide geotechnical investigation for that rather than a specific point load for mobile cranes. And a nice intermediate to them is their sheet pile walls, your tower crane foundations. They're slightly more widespread, but still within a certain area of the site. So that's the obvious kind of areas where you definitely need geotechnical investigation. But things that more people forget about is if you've got some backpropping that's holding up a structure, you still need to consider the foundations of this backpropping or the facade retention system. As you can see from that photo on the left, you've got quite a lot of cartilage just at the side there. So you need to ensure that the ground underneath that can hold up the weight that you're adding on that wasn't part of the original building design and is outside the foundations of that building. Or even if you're inside the building, like on the right, this building had strip foundations, and so we were loading a bit that had not had foundation loads, and we're redirecting the loads from walls into the center instead of keeping it on existing foundations. So we need to know what the ground underneath these things are before we can make an informed design, and so that we don't have to cast massive foundations for absolutely everything we ever do. So when you're getting the ground investigation, there's lots of different types, and having accurate ground investigation is invaluable for everything you do. Instead of, yes, just throw in 5 meter cube of concrete and be done. Maybe the ground that's already there is fine. But sometimes you have to just run with what you've got. So classifying the goodness of the ground investigation, we'll start from worst and we'll work towards what we prefer as designers. So just photo of the ground. Now getting accurate ground investigation from that picture, we can get a much better idea than just looking at the ground. We can see that that's a bit cohesive. It's got something on top. It's definitely got water there. So you can get a lot of information from that, but it's only really good to get an idea of, is it granular, is it cohesive? From this picture, you can see it's quite a steep angle, so probably got some strength in it, not just sand at the beach. And you can get an idea of, will a batter work, will a batter not work, that kind of thing. But it's not the most useful thing if you're going to rely on these geotechnical properties for a design. Uh, the next step up would be going to historical borehole logs. Obviously, borehole logs, good thing to use. We've got the nice descriptions. Sometimes the descriptions are, shall we say, old-timey. I've come up with phrases that haven't been used in the last 50 years, but these give an idea of what the ground is like for someone who's actually had a proper look at the ground and we're not just relying on photos. That is good, but as you know, on site, sometimes you just dig up a mass amount of ground, backfill, and we don't know if that's happened since these borehole logs have been done. Sometimes these borehole logs go back 100 years, maybe more. Just any historical borehole logs are very good, but can be outdated and still not the best representation. But moving on from that, if we have up-to-date borehole logs, something that's just been carried on site, we can get a lot more detailed information. So the descriptive logs give a lot about soil classification. There might be some reference to density, or if it's a soft clay, a firm clay, if the granular material is dense or loose. And we can take that information, and it is quite subjective. There's minor discrepancies in what you can take. A soft to firm clay that can have a wide range of what it can be. Maybe it's at the very top, maybe it's at the very bottom. But as engineers, we tend to take conservative approaches to these things. So we'll go to the bottom just to make sure everything stands and is not going to fall down. But moving on from that, tests of the actual soil material. So this is a borehole log that has a bit more information in it. You've got some soil properties on the side. Shear strength is taken out, so you've got some hand shear vein test results. You can get standard penetration results, and these can be represented in standard borehole logs, or you can have them done separately. All of the more information we have on this, the better and more cost efficient our designs can be. And obviously you've got CBR tests. They can be done typically on haul roads and things like that, or in site-wide things, and plate bearing tests, which I love to see. I love a good plate bearing test, but they do have their limitations, and I'll talk about them later. But moving on from actual on-site testing, you can send things to the lab. Now, this is where we get the proper results, the good results. This is a return from a lab test that we had a while ago, and you can see this is the number that it is, 22 degrees, perfect. Cohesion, no cohesion, that's okay. Now that we know, we can base our design on that. Shear strength, when we know the shear strength, we can just absolutely just plug those numbers in the design, and in that one location, we know this will stand. When you're going across the site, if it's not one location, like those crane outrigger tests, sometimes you have to be more conservative. If the test is half a mile away, you have to be quite conservative with the numbers you take. You don't know what changes in half a mile. You don't really know what changes within 10 meters. But when you've got an actual test that's been lab tested at the very location that you need to put something, you can be quite confident that your design is going to be as cost effective as it can be. So all of these methods, although they're good and you get actual results for it, you still need someone competent to come in and look at it and go, yes, this is what we need to use. Yes, this is exactly the information we need to consider for this design. And as Josh mentioned earlier, if you've got this information, sometimes you can look at it and go, no, this ground is good enough that you don't need any temporary works. You don't need to import countless meter cubed of fill into site to replace this ground. This ground is as good as the fill we're going to put in anyway. Maybe you just need to strip back the top layer of soil, which happens rarely, but when it does happen, it's great. Other things to consider is when you have a ground investigation, it's all very good if you go down and you get, oh yes, the soil's great, and then half a meter away there is a low pressure gas main, and if you actually load it to what you think you can, you might just ruin some services, and then you get into very big problems of oh no, all the gas in Manchester has been turned off. We've not done that yet, but it's been known to happen. So fingers crossed we don't do that. But if you get a gas or a water service map like this one is, you can see where the services and any buried structures are, and hopefully you can pinpoint where all these things are. But if this is just a generic one, unlike this, where it says, yes, the water pipe runs through here, sometimes they can be inaccurate as well, and you have to go to site and you have to figure out exactly where the pipes are. Sometimes this can be done in unobtrusive tests. Sometimes digging a bit gets you the answer, but knowing exactly where these pipes are on your site or any services, electrical services, what have you, that gets you a lot of information and you know exactly where you can put large loads onto the ground there. Sometimes you get more interesting things like unexploded ordnance. There's some good unexploded ordnance maps, and you need to make sure you stay far away from where they can be and make sure you don't disrupt them unduly. So all of these things make for better and more concise designs, as we were speaking about earlier. So what we want as designers, ideally, is the lab tests. We need to know if it's a granular material, the internal angle of friction of the soil. There's rough correlations between SBT tests, as shown at the bottom there, and the internal angle. So if we have SBT tests that are done on site, we can infer internal angles instead of sending it off to the lab. For cohesive tests, we can do hand chain veer tests just into the very soil that we're actually going to be using, and that gets you undrained shear strength very easily, and there's a correlation between SBT and that as well. And if not, then a descriptive log can get that. You can see them at the bottom right there. Medium dense sand can get you 100 to 300 kilonewton per meter square capacity, but that is a wide range. If you actually have the information of what it is, maybe you can take the 300, maybe you can only take the 100, but if we don't have that information, we're going with the 100. Just to be conservative, but having the information means it's far easier for everyone. You can get more cost-efficient designs. Sometimes the water table is very high on site. Sometimes it comes half a meter up to below the ground level and then reduces back by 5 meters. If you happen to be on the coast, you have to be aware of what the water is going to be doing, because that can have a very, very big impact on the strength of granular material. Sometimes the stiffness is critical for the design, so we need to know exactly what the ground is. For these facade retentions that I was showing earlier, you need to know that when you put all that cartilage on the ground, it won't move and then cause the building to crack as it settles itself over how many months you're going to have that there, or how many years you're going to have that there. So we want to see all of these things when we're designers, the relevant ones, and we want the most accurate information we can, because then we can get the most cost efficient and elegant designs that are possible for that area. And we always like an elegant design. The bane of my life, limitations of plate bearing tests. Now this comes in a lot because sometimes you get a big site, so you think, okay, what's the easiest way to get a ground investigation of this site? And it's, oh, we can do CBT tests or plate bearing tests all over the site, and then we'll send that back. And the problem with CBR tests and plate bearing tests is that they only really look at surface levels. So if you are a meter down from the surface and you're doing a 450 mil diameter plate bearing test, a meter down, you've only really got less than 10% of the load a meter down. So if you've got some services that are a meter down, you can get a feel for that. But if you go any further down than that, you have no idea. So if you know that 2 or 3 meters down, you've got a very soft clay, you don't really know how much a tower crane is going to load that, or a crane outrigger, as I've shown here, because that's a very high point load. So if we've got a 2 meter square crane outrigger mat and we go a meter down, and a meter down it says, oh yes, it's fine. There's no problems here. And then we go twice that, and suddenly you're into soft clay and everything just starts to settle a bit and there's lots of movement. It's not going to be good. So plate bearing tests and CBR tests, there's a time and a place for them. And it's time and the place for them is when all your information needs to be close to the surface. For example, if you're testing a newly constructed pile mat or a working platform and you want to see if it's acting in the way you think it is, if the formation level ground is what you thought it was, and if you're checking compaction of the surface level designs and things like that. So it's very important that the right tests are used for the right places, and the more information we have, the more elegant our designs can be. So I think that's me done. Oh no, I've got an example as well. Of course, I stuck this in at the last second while no one else was looking. So an example of it is the crane mat. So the thickness of crane mats can vary a lot on internal angle of friction in this example. So what we had originally was we didn't know the underlying ground. So we've got underlying ground beneath outrigger loads. And then we've got Eki mats underneath the outrigger. And then we needed a 700 mil platform underneath that when we were just taking it on visual inspection of the ground. And then we went and we got the plate bearing test that we needed. And suddenly the mat goes from 700 mil to 300 mil in the final design. And it was clear that we were being conservative in the first design, and then we moved over and we got the actual results from on-site testing, and we were able to do a much thinner and more elegant design. This lift went out without a hitch, so we know that the 300 did work in the end, and the site investigation was good. But we had to be conservative when we were starting out because we didn't know what that underlying ground was. So hopefully that gives you an idea of why it's important, and I'll hand back to Josh and he can sum everything up in the entire presentation. Josh?
Thank you very much, Richie. So just to sum up what we've covered today, what makes good site investigation? Essentially, for me, it's providing succinct and accurate information. It's not providing lab results for the whole site, getting hundreds of tests and providing them for a particular crane. It's thinking, okay, the crane's going to go there. Let's get a trial pit using the existing site investigation that we've got, and then let's do some plate bearing tests on top of that, and keeping it simple and making it commensurate with the risk. Commensurate with the risk means if it's something that's high risk and is going to involve a high consequence of failure, so it's got a high implementation risk, then we need to provide more resources, and which means more thorough testing, etc. Whereas if it's very low risk, then a trial pit, like Richie said at the beginning of his, would suffice. We can guess what the we can make an estimate, a conservative estimate of what the properties are, and that may well be sufficient for what we're doing. So it's providing succinct and accurate information for what we are, the task at hand. Some other ones that I've noted on there is highlighting risk, which leads to increased safety and timescale, thinking ahead so you can get the most out of your site investigation, as opposed to leaving it last minute and then you've only got a certain amount of a certain amount of options available to you. And then what Richie's last example demonstrated to me was that conservative consumptions result in more conservative design. Linking back to what Adam said as well, the GIGO, garbage in, garbage out. If we're getting very poor information on the ground or on the structure, then our hands are tied really in terms of what solution that can be provided for the project team. So site investigation, essentially it's so we can understand the problem and therefore get the correct and most efficient solution. Okay. And that's it for today. So some other resources there that we've noted if you would like to know a little bit more. So we've got Temporary Works Forum with some really good resource on there about constructability, Temporary Works, Principles of Design and Construction, some good information there. There's our YouTube channel as well. Lots of information on Temporary Works as a whole on there too. So